back to this course on computational thermodynamics and kinetics of materials. Today we will see a slight variation in kinetic simulations. This is what it is going to be. We are going to see some modified version of shell solidification. We have already done the simulation for shell solidification. We will see what is this modified shell solidification considering two different scenarios, that is back diffusion and solute trapping. Okay, so recall this shell solidification where the assumptions were these two: infinite diffusivity in liquid and no diffusivity in solid. This is what we have focused on and did the simulation when we did the shell solidification. Okay. One important idea that we did not discuss much about shell solidification is the local equilibrium. Let us understand that. Okay, if you see this non-equilibrium cooling or shell solidification, what we have been discussing is this kind of thing, where at high temperature when liquid becomes solid, so this is in the copper nickel system, we have seen this also as an example before for non-equilibrium cooling. Recall this. So where we have this initial solid forming, according to this tie line, the solid should have 46 nickel in this case. Now when we go from this temperature to another temperature rapidly, what happens? Non-equilibrium cooling happens like this, where according to the tie line, the solid should have 40 nickel. If it is equilibrium cooling, it should be 40 nickel everywhere in the solid. But what happens is, a 40 nickel layer forms on top of solid which is 46 nickel formed at higher temperature. Okay, so the inside here it is 46 nickel, outside it is 40 nickel. So therefore, a cumulative average composition of the solid becomes 42 nickel. Okay, so this is what the solid's composition is if we do non-equilibrium cooling. Now what happens to the copper? If it is only 40 nickel, 60 will be copper, right, in the solid. But when nickel goes to 42, copper will be only 58. So that extra copper has to go to liquid. The liquid composition keeps changing because of this no diffusion in solid. Okay, if these layers are going to stay like this with 46 nickel and 40 nickel like this, then the liquid composition is going to get increased more and more in copper, so that non-equilibrium cooling will be happening. And in the shale, it was happening to such an extent that in an overall composition where we do not expect any eutectic reaction, it ends up undergoing an eutectic reaction. So we have seen that example, if you could recall that. Now this particular line that you see, the outer layer, is having 40 nickel. This 40 nickel is according to the equilibrium tie line. So although equilibrium tie line composition is not followed for the entire solid, the solid which is touching the liquid, the outer layer solid, should have the composition indicated by the equilibrium tie line. So that means this is local equilibrium. Okay, only at this outer layer the solid has the composition indicated by the tie line. Okay, liquid also should have the composition indicated by the tie line, and that is called local equilibrium. Okay, so local equilibrium exists at the interface in shale solidification as well. The solid and the liquid at the interface have the composition shown by the tie line. So this is an important aspect of shale which we did not discuss in detail that time. Okay, this is important now for this class. So local equilibrium exists at the interface. This is another condition in shale solidification. Now what is this back diffusion that we are talking about? It is important in solidification of most cases where diffusion in solids occur. Okay, we call it back diffusion because interface is moving forward and the diffusion is happening within the solid. Okay, these 40 nickel and 46 nickel different layers are going to become homogenized. So that is called back diffusion. So diffusion in solids occur. If we consider this, then how this diffusion is going to happen? It is going to be according to the mobilities, basically the diffusivities, cooling rate and diffusion distances, isn't it? Cooling rate you can understand. Basically at different temperatures there will be some time exposed. It's not that isothermal diffusion is going to happen. As the temperature changes, for different temperatures different mobilities should be considered and the diffusivities should be calculated and diffusion should be understood. So cooling rate is going to affect this diffusion, and diffusion distances, they also matter. If you consider a solid growing in liquid like this, let's say this gray one is liquid and this white one inside is solid. Okay, So this is how the solid will usually grow. This is called a dendritic growth, and you can see a primary dendritic arm, this middle one, like a knife. This is the primary dendritic arm. From there, the branches are happening like this. These are secondary dendritic arms, and between two secondary dendritic arms is where the liquid is captured. Okay, so if you expand this small region, create them as the domains in the diffusion. Let's say this is solid and this is liquid, and this interface is going to move so that liquid is consumed by the solid as solidification progresses. So if this happens, how much of this diffusion distance is important, you can see here, because this liquid regime is the total area to which this can grow. Okay, so from here, it can go to the middle here, and this dendritic arm can go from here to here. So the diffusion distance is controlled by this secondary arm spacing. Okay, that is also important. So that solidification with back diffusion can be understood. Right? If the cooling rate is fast cooling rate, then back diffusion will be less. Solidification is similar to the classic shale because back diffusion is less here. Or if it is very slow, then back diffusion will be really high and it will be almost like the equilibrium cooling. Okay, these are some extreme cases of cooling rates. Let's summarize our understanding on this back diffusion. There is infinite diffusivity in liquid, local equilibrium exists at the interface, and diffusion in solids is according to mobilities, cooling rate and diffusion distances, that is basically secondary dendritic arm spacing where the liquid is trapped. Okay, there are empirical models for different materials. Experimentally observed interdendritic arm spacing is figured out, and based on that there can be some models that can be used, empirical models that can be used to get this part, diffusion distance part. What is important is mobility and cooling rate. We have done a non-isothermal simulation in the last class. So cooling rate is basically going to give a non-isothermal profile for temperature. We have to bring that into picture and use mobilities, then do the simulation. Okay, let's do that for this one, modified shale solidification for aluminum copper alloy, aluminum 4% copper alloy. So this is aluminum copper phase diagram, and it is focused on aluminum rich side where this 4% copper line is given. You can see this is definitely before the eutectic. So according to equilibrium cooling, we should not see eutectic reaction, but shale thing will give eutectic reaction. And if back diffusion is allowed, what will happen? We can explore that. So we can say shale with back diffusion in primary phase. Primary phase is the first phase to solidify. We are going to allow back diffusion in that. And as we said, cooling rate is going to matter a lot. We will do a different cooling rates, 10, 1, 0.1 and 0.001 Kelvin per second, and visualize the results along with the equilibrium cooling. Let's do that. We'll keep default setting for other parameters. Okay, so for this we have to choose this non-equilibrium shale solidification, not the diffusion demo. Although this shale solidification with back diffusion requires diffusion data, we are going to use this particular template, not this diffusion demo. Okay, so click on shale solidification. Okay, and here in the package, select AL demo, MAL demo, because we need diffusion data for the simulation. So select both. Okay, then select elements aluminum, copper, both are selected, then go to shale calculator, set composition of copper as 4 mass percent, 4 composition unit is mass percent. All right, then let the remaining settings to be same except this classic shale. Instead of this one, we are going to use shale with back diffusion in primary phase, this one. Okay, so click on that. Okay, so cooling rate, we can set up different cooling rates. Let this be 10 Kelvin per second. 10 Kelvin per second is reasonably fast. Okay, we'll keep that, and then we will create 3 more cloned versions of this. Clone shale calculator 2. This is going to have 1 Kelvin per second, and we are going to clone it again. This is going to have 0.1 Kelvin per second. Clone it again. In this, I'm going to have 0.01 Kelvin per second. Okay, so now 4 shell calculators are there in decreasing order of cooling rate. Okay, this is the slowest shell calculator 4. If you want, you can rename these things with the cooling rate. Okay, I'm proceeding without that. Okay, go to plot renderer. Make all the shell calculator as predecessors. Add predecessor shell calculator 2, add predecessor shell calculator 3, add predecessor shell calculator 4. So all shell calculators are linked to one plot renderer. That's all. Let's just perform. Okay, so now if you open the plot renderer and see, you can see 4 different lines coming here. If I zoom into this region, you can see 4 different lines. Okay, the one on the right extreme is obviously the one with the slowest cooling rate. You can see here shell calculator 4 results are this one. Okay, so if you reduce the cooling rate further, it will go even towards the right. This is the equilibrium solidification line, and these are all with the back diffusion. But even with the back diffusion, we are seeing Al2Cu C16 plus FCCA1 in all these cases. So what does it mean? It is becoming flat like this, meaning at one temperature entire liquid becoming solid. So that is eutectic. That is happening in all these cases. So it is still very much closer towards the shell, even with 0.01 Kelvin per second. If you reduce the cooling rate further, it will further move towards this equilibrium. Okay. Right. Okay. That is shell solidification with back diffusion. Let's understand one more idea called solute trapping. What is this solute trapping? You may be thinking, in this shell itself we said in solid there is no diffusion. So as if solutes are already trapped. Okay, then what is this new thing again, solute trapping? This solute trapping is different. This happens at extreme fast cooling scenarios. Let's understand that. When we said local equilibrium exists at the interface in shell, we meant this partitioning of elements to solid and liquid according to tie line. So I am putting a new word here, partitioning. It's nothing fancy. If you look at what happens to a liquid when it becomes solid, the solid and liquid interface has the composition indicated by the tie line, right? So tie line tells you what should be the distribution of elements from the overall composition to these two different phases. That is partitioning of elements. Okay. So we can even put a partitioning coefficient Ke, which is Cl by Cs, liquids composition by solids composition. So we have seen this, right? So solid composition and liquid composition at the interface will be according to the tie line. That is what we have assumed in shell solidification. Okay, so this the overall composition, let's say, is somewhere here. This is the rest of the liquid as this composition. That is possibly the initial overall composition, and that is getting distributed to liquid like this. It gets enriched in the liquid at the interface and depleted in the solid at the interface. Okay, this is the redistribution, and obviously this requires diffusion to happen, right? There is some rearrangement of species here, so that requires some time. What if solidification is too fast and that time is not available? Okay, so solidification in very fast cooling scenarios, something that we see in processes such as additive manufacturing. Okay, this additive manufacturing, if you have not come across this before, also known as three-dimensional printing, 3D printing, is a free-form fabrication process by which the product is built up, the engineering component is built up, layer by layer deposition of material. So layer by layer powder will be deposited and the powder will be melted. One more layer will be melted on top of that. So like that the entire material is built. So in this process, every layer is getting cooled in an extreme fast manner. Okay, because of that, solute trapping can happen. What is this solute trapping? The local equilibrium at the solid-liquid interface, what we assumed in the shell, it breaks down for such solidification rates. That's the problem here. Interface velocity is high, so high that it traps elements before proper partitioning. That is solute trapping here. At extreme cases, the liquid composition becomes solid compositions. Whatever is the liquid composition here in this point, it directly transforms to solid composition. Okay, so in that case, the partitioning coefficient depends on the interface velocity. So we can compare these things and understand it. You see, solute trapping can be negligible in this case, where Cs by Cl is according to the partitioning coefficient given by the tie line. Okay, this is partitioning coefficient. Now if it is a significant, if there is significant solute trapping, this can happen when interface velocity is higher compared to this case. So when the interface velocity is significant, solute trapping is significant, then Cs by Cl is more than Ke. Solid actually traps more solute. It's supposed to have very less solute. It now traps more solute. So concentration of that solute in the solid is now high. Therefore, the ratio is higher than the equilibrium partitioning coefficient. And when it is complete solute trapping, the interface velocity is extremely fast, then whatever is the composition of liquid becomes the composition of solid. So the interface moves so fast that no diffusion can happen to redistribute the solute into solid and liquid. So this is complete solute trapping. And the solute trapping, as I said, is very important in process such as additive manufacturing. If you are interested, you can run some examples with regard to solute trapping and see. I'll just run one example and show you. Okay. Go to these example files. Not to diffusion module, because solute trapping doesn't require any diffusion to happen. Go to thermocalc, this one. Okay. Here, share with solute trapping. You can click on this, share with solute trapping, and open it. Wait for a few seconds. Okay. So now you can see in aluminum silicon copper system, this solute trapping is attempted. You can see in the databases, diffusion database is not even selected here, because that doesn't matter. Now this solute trapping is going to depend on the scanning speed. That's the scan speed in additive manufacturing, where the powder will be melted by this layer by layer deposition, right? So that scan speed is given here. This alpha is some kind of an angle. So different process parameters like that are given here. Okay. The fundamental side, I want to tell only one thing, that is the model used. This is the ASIS model for solute trapping. So detailed discussion is there in thermocalc user guides. You can check it out later if you are interested to know further. Okay, and of course the most important thing to select is this shell with solute trapping. This is an important option to choose. Only after choosing this you will get all these options to enter. Okay. Now that is done, and it's connected to shell solidification plot. And classic shell is also done parallelly, and it is also connected to the same plot. And after performing, you can see here both the curves along with the equilibrium one is there here, dot dot. The blue one, okay, the blue one is the classic shell, and the red one is the solute trap. You see, solute trap, as I said, may be extreme fast cooling, but by this extreme fast cooling you should not expect that things will be as close to the shell as possible. Okay, it is extreme fast cooling, but it is increasing the concentration of the solute in the solid. As per shell, it should be low concentration of some solute in the solid, but because the interface is catching up with the liquid, it doesn't allow the solute to get redistributed. The solid's composition is getting further, therefore the liquid is not solidifying lately as in the shell case. So it gets solidified fast. Therefore, the solute trapping is somewhere between the shell and the equilibrium. This is how it comes. Okay. It's a quite interesting phenomenon. Thank you. I hope the lecture is useful. See you in the next class.